In Chapter 4, Section 1, we'll look at maximum and minimum values to include global maximums, global minimums, and local maximums and local minimums. So just to give us an idea, let's say we have a curve and let's just say it looks like this. Well, what we're going to do is we're going to zoom in on a portion. So we're going to say, okay, let's look from here to here. And we're going to call this A and this B. Well, clearly there's a local maximum right here. Local max. And there's a local minimum right here, local min. Now it turns out that the local minimum is also the global minimum because it's the lowest portion of the function in this green window. But this local maximum is not the global maximum because this point right here is higher than everything else. So right at the end of this interval, we would say that point is the global max. So when we do these, we're going to have to check typically at least 3, if not more, points. One is we're going to check f of a. So what does that equal? Now in this one, f of a would have been right there. It's the y value when x is a, and that one's not the highest and not the lowest, so it's not a global or local min or max or anything. We found the local minimum, so we'd say that occurred at point C, and we found the global maximum occurred at point B. So we have to find f of a, we have to find f of b. And then how do we get, actually let's label this. So I've got 2 points, C1 and C2. Those produced this local max and that local min. Well, what's unique about those 2 points? What's unique about those 2 points is that the slope of the tangent line is 0. And we recall that the slope of the tangent line is a derivative. So the derivative of the function at C1 is equal to the derivative of the function at C2. Those are both 0. So what we're generally going to do is we're going to take the equation, find its derivative, set it equal to 0, find any C's, C1, C2, C3, and then we're going to plug those back into the original equation to find these max and mins. And then we always check the endpoints, A and B. Okay, so that's the idea. So let's take a look. Problem 1 is going to walk us through it. So it says we have this function, and I'm probably just going to do the whole thing without stepping through it, each box. So it says the function is equal to x to the 3/5 times 4 minus x. And so what they did is product rule. So they said, what's the derivative of this function? Product rule says take the derivative of the first thing, so it'd be 3/5 x to the 3/5 minus 1 times the second thing left alone, 4 minus x, plus leave the first thing alone, times the derivative of the second thing, which would be just minus 1. So we end up with, this is going to be 3 over 5 x to the 2/5, and then it's going to be 4 minus x on top, and then this one's just going to be minus x to the 3/5. So let's see, what did they want? They wanted this minus 1 here, and they wanted the 3/5 x to the minus 2/5. They wanted that part here. So notice 3/5 minus 1 will be minus 2/5. Then they're going to distribute this minus 1 and just write this again. And they're going to rewrite this as I've started to. So they have 3 times 4 minus x on top and 5x to the 2/5 on bottom plus the negative x to the 3/5 over here. Okay, now they're going to make a common denominator of 5x to the 2/5. So let's pick up where I had stopped. So f prime is going to equal 4 minus x minus x to the 3/5 times 5x to the 2/5. And what that allows us to do is put this all on top of 5x to the 2/5. So it's just creating a common denominator. So we'll multiply and divide the right term by 5x to the 2/5. And we'll get f prime of x equals 3 times 4 minus x minus 5. Now this is nice. X to the 3/5 times x to the 2/5 is the same. Give myself a little more room here. This was 5x to the 2/5. On the numerator, you get x to the 3/5 plus 2/5. So when you multiply the same base, you just add the exponents. And then we still have 5x to the 2/5 on the bottom. 3/5 plus 2/5 is 1. So this is just 5x. So we're going to get, distribute the 3, 12 minus 3x minus 5x all over 5x to the 2/5. Or finally, simplifying completely, we're going to get 12 minus 8x on top over 5x to the 2/5 on the bottom. That's what we have right here. Okay, now, as I had pointed out, this thing's going to have, and I should have mentioned this earlier, those are called critical values. So C1 and C2 are critical values. Those occur when the derivative is equal to 0. So we set this thing equal to 0. Now, I can multiply both sides by 5x 2/5, and I still get 0. So really, all I care about is when the numerator equals 0, or when 12 equals 8x, or when 12/8 equals x, which is the same as 3/2. And I think that's everything here. So the numerator is that. We set it equal to 0, so we get x equals 3/2. And so and there's a point where the function does not exist. So notice back here, right back here, if x equals 0, the derivative of 0 would be 12 over 0, which does not exist. So we're going to also restrict x equal to 0. I shouldn't say restrict, because x equal to 0 will actually work in the original equation. In the original equation, f of 0 is 0. In fact, you can see it in the picture. It's right there. But notice its derivative is a vertical line. So the slope of the tangent line is a vertical line which has an undefined slope. So we would have this 0 would work in the original equation, but not in the derivative. So it's a point of interest. So we were going to record the thing does not exist when x equals 0. And those are the two critical numbers. So the critical numbers are 3/2 and x equal to 0. Because they either make the numerator of the derivative 0 or the denominator of the derivative 0. And that's problem 1. Problem 2 is also going to be similar. So they're going to walk us through it step by step. I'll probably just do the whole thing. So we're given a function, f of x equals x cubed minus 3x squared plus 2. The derivative should be easy to calculate. It's just 3x squared minus 6x, and we're going to set that equal to 0, factor out a common 3x. So this is 0 when x is 0 or when x is positive 2. And let's see, so we did the derivative. we found 0, we found 2. Let's see here, these are critical numbers. Oh, then we have to figure out what is f of 0. So now we're going to plug 0 into the original equation to find out what its actual value is. So we're going to get 0 cubed minus 3 0 squared plus 2. So that equals 2. And then f of 2 would be 2 cubed minus 3 times 2 squared plus 2. And if you do that out, you will get negative 2. And that's those two answers here. Okay, then we also have to check, so the interval is -1/2 to 4. So that's A and this is B. So we also have to check f of A and f of B. So f of A is f of -1/2, which would be -1/2 to the third. Notice I'm plugging these into the original equation, not the derivative. -3 times -1/2 squared plus 2. And if you do that out, you should get 9/8. Then we're going to check f of B, which is f of 4, which is 4 cubed minus 3 times 4 squared plus 2. And if you work that out, you get 18. Now we have to compare these four numbers. Now we say, what's the biggest, what's the smallest? Well, this is the biggest, the max, and this is the smallest, the min. So we're going to say this has a maximum value when x is 4 and the value is 18. It has an absolute minimum when x is 2 and the actual y value is -2. So that's pretty common. We'll check the derivative x values, and then we'll check these the interval x values. So the lowest number in the interval and the highest number in the interval. And so like I had started off with, we're basically boxing in. We're saying, okay, I'm making a box like this. And in that box, I want to check what's the highest value, what's the lowest value. And so we find this is the highest, and this is the lowest right here. Okay, that's problem 2. Okay, problem 3 is just a picture. So we got this kind of funky graph going on. There's some holes, there's some gaps, there's some sharp corners. So this thing is not continuous. It's not differentiable on the entire domain. So any gap, any sharp corner is not differentiable, and any hole or gap is not continuous. But we can still look at what's the highest point, what's the lowest point. So we can say the absolute maximum, if I just look at this picture, the highest it ever gets is right there, which is a value of 5 units up. So we'd say the absolute max is 5. The absolute minimum value, so this one's tricky. This would technically be the lowest point, but because it's a hole, it's not going to count. And the reasoning is, so this hole occurs at -1. So it can't be -1 because it's a hole. But then you say, okay, so my minimum is -0.9999. And then I say, okay, I got you beat. My minimum is -0.999999. And then someone else says, oh, I got you beat. The minimum is -0.999, and they just keep listing 9s. So we can't ever agree on this, so we say the minimum, absolute minimum, does not exist. Okay, now for the local max values. So this is a global max, but it's also a local max because it switches from increasing to decreasing. So anytime you have a hump like this, you're going to have a max. So it's a local max and it's a global max. The difference being, in the first picture I drew, or even the last problem, if your graph looks like this, well, this is a local max, but it's not global, because there's the global max right there, the highest point. So any hump you have is a local max or min, a hump or valley, but it will not necessarily be also the global. Okay, so we have a local max also at 5, because it is a hump, and then we also have one at 4. So we would have, so this one's also interesting because this has a hole at 4, so that one doesn't count, but this one is a hump that ends right there at 4, so that's why we get 5 and 4. Okay, local mins. So we're going to look for humps again. So we have a valley at 2. So that's this number here. But then we also have a sharp corner, which can count as a min at 3. So we're going to get 2 and 3 for the local minimums. And that's problem 3. Okay, in problem 4, we have to do the derivative of this function. So we're going to have g prime of y equals, this is a quotient rule, so we have to use f prime g fig minus gif g prime f over g squared. Now, the derivative of f prime would be the derivative, well, let's write it. F equals y minus 5. F prime is very easily 1. G is y squared minus 3y plus 15. Therefore, g prime is 2y minus 3. So we replace this with these 4 different terms. F prime is 1. G is y squared minus 3y plus 15 minus g prime, which is 2y minus 3, times the original f, which is y minus 5, all on top of g squared, which is y squared minus 3y plus 15 squared. Okay, g prime. We've got to distribute all this stuff on top. We're going to have y squared minus 3y plus 15 minus 2y times y, which is 2y squared, minus 3y, but with another minus, so it's plus 3y, minus 10y, 2y times 5, but it's double negative, so it's plus 10y. Then it's minus 3 times minus 5, which is plus 15, with a minus, so it's minus 15. And the bottom is just y squared minus 3y plus 15 squared. On top, we're going to have y squared minus 2y squared, which is minus y squared. So we got that term and that term. We have minus 3y plus 3y, so minus 3y plus 3y will cancel, which leaves us plus 10y. And then we have plus 15 minus 15, which cancel. So that's it on top, y squared plus 10y. And then on the bottom we have the same thing, y squared plus minus 3y plus 15 squared. Okay, now we care if either the top or bottom are 0. So we're going to set them both equal to 0 and try to solve for y. So let's solve the top for 0. So we'd factor out a y and have 10 minus y on top. And on the bottom, you can't factor that. And if we just look at y squared minus 3y plus 15, it doesn't factor, and you'll find that there's no value of y that makes that equal 0. So this is not going to equal 0. So in the bottom, we have no issue. It's never going to equal 0, so we're just going to ignore it. So all we're going to care about is the top equaling 0. There's 2 points where this is 0. If y is 0, or if y is positive 10. So those are our 2 critical values. And I guess that's it. So they just wanted to find the 2 critical numbers. They're 0 and 10. Okay, so that's problem 4. Find a derivative, say equal to 0, top and bottom. Look for those critical numbers, and we found 2 in the numerator, y equals 0, y equals 10. Okay, for problem 5, it's going to be a little different. We have this function, and it's 4x cubed minus 12x squared minus 96x plus 7. And they want this on the interval minus 3 to 5. So that's A and that's B. The very first thing we should find is the derivative. So that's going to be 12x squared minus 24x minus 96, and we're going to set that equal to 0. Now it turns out that you can divide all those terms by 12, so you can get x squared minus 2x minus 8 equal to 0, because 0 divided by 12 is still 0. This will factor into x minus 4, x plus 2, which gives us two critical values, 4 and negative 2. Now, you want to check and make sure that those are both in the interval. So 4 is in between minus 3 and 5, and negative 2 is in between minus 3 and 5. So we're going to have to check all four numbers. So we're going to plug in f of a. We're going to plug in the next biggest number, which is minus 2. Plug in the next biggest number, which is 4. Plug in the next biggest number, which is 5, the endpoint. And we're plugging them into the original equation. So it would be minus 3 minus 5, plugging it into this one, over minus 3 squared minus 3 times minus 3 plus 15. And if you do that, you will get f of negative 3 is 79. And that's the only one I'm going to show as a substitution step. So I can imagine you'll be able to plug in minus 2 into that equation, and 4 and 5, and you should get 119 when you plug in minus 2. You should get negative 313 when you plug in positive 4, and you should get negative 273 when you plug in positive 5. And we just have to look, and we would say the biggest of these four numbers is 119. The smallest of these four numbers is negative 313, so that's our min and max. And we just have to outline them: minimum, minus 313, maximum, 119. And so that would be how you do number 5. Number 6 is going to be pretty much the exact same thing. The equation is going to change though. F of t is equal to t minus, and I'm going to write this a little differently, t to the 1/3 power. And the interval is from minus 1 to 5. So that's A and that's B. Immediately find the derivative. So the derivative of f would be 1 minus 1/3 t to the minus 2/3. So again, power rule, bring the power down, subtract 1 from the power. And so what we get is this equals 1 minus 1 over 3 times, let me write it as t to the 2/3. Okay. Now we're going to set that equal to 0 to find critical values of t. So we can add this 1/3 t 2/3 to both sides, so we get 1 is equal to 1 over 3 t to the 2/3. And now we're going to multiply by 3 both sides. And then we're going to flip both sides, so we're going to get 1/3 equals t to the 2/3. And then we're going to, okay, so this is good practice. How do I get rid of a 2/3 power? To get rid of a 2/3 power, you raise it to the 3/2. So it's basically taking it to the reciprocal power. So if this is 2/3, you flip it, make it 3/2, and you raise it to that power. But if I do that, I have to do that here as well. So this is 3/2. Okay, so what's that going to do? We're going to have 1 to any power is 1. So this is 1 on top, and this is going to be 3 raised to the 3/2 equals, I'm going to write this out, I probably won't show this ever again, but this is 2/3. When you take a power to a power, you multiply them. So this is times 3/2. But that's the same as t to the 6 over 6, so multiply across, which is the same as t to the 1st, which is the same as t. So what is 1 over 3 to the 3/2? So 3, this is the same as the square root of 3 cubed, which is equal to 1 over the square root of 27. Okay, so that is our critical value. So now we have to test all these three numbers. So f of minus 1, f of 1 over root 27, and f of 5. F of minus 1 is going to be minus 1 minus minus 1 raised to the 1/3 power, which is just 1. So you're going to get, this is 1 minus 1, this will end up being plus 1, which is 0. This is the tricky one. 1 over root 27 would be 1 over root 27. So again, I'm plugging into this formula now. The original equation, not the derivative. So it's 1 over root 27 minus, this would be 27 raised to the minus half raised to the 1/3. This would be 1 over root 27. This would be minus 27 raised to the minus 1/6. Is that going to get us by us anything? I don't think it's going to. So instead, let me do this a different way. Because a power raised to a power is just multiplication, we can flip the order on this and call this 27 to the 1/3, then raised to the minus 1/2. And 27 to the 1/3 is just 3. So this is 1 over root 27 minus 3 raised to the minus 1/2, which is 1 over root 27 minus 1 over the square root of 3. All right, let's actually delete this one for now because we need more room. Okay, so we need a lowest common denominator, so we're going to multiply by square root of 3 minus root 27 over square root of 27 times 3. This is going to be 27 can be written as 3 times 9. Oh, this is easier than that. This is the square root of 81. Let's do it that way. So we get square root of 81 minus root 27 over square root of 81. And that's going to be root 3 minus square root of 27 over 9. I'm trying to get to the final answer like I have it written. And that's going to be, okay, so we can run out of room. Root 3 minus 27, which can be written as 3 times 9. So the 9 can burrow out of here as 3. Jeez. It's all just algebra though. So it's going to be 3 root 3 over 9. 1 root 3 take away 3 root 3s is negative 2 root 3s all over 9. So calculus is the easy, well, maybe not easy, but it's not the hard part of this problem. It's just fractional powers, negative fractional powers, and coming up with the simplified answer. Okay, but we're not done yet. We have to also plug in f of 5. So f of 5 will equal 5 minus 5 raised to the 1/3. And it helps to come up with decimal values for these things. So let's see, our first one we tried was -1, and we got 0. and f of 1 over 27 was negative 2 root 3 over 9. But I don't know what's bigger, 5 minus 5 to the 1/3 power, or minus 2 root 3 over 9, or 0. So it helps to come up with a decimal equivalent, even though that's not the answer you're going to type in. 5 minus 5 root 3 is approximately 3.29. And negative 2 root 3 over 9 is approximately negative 0.385. So based on this, we can see that this is the smallest number and this is the biggest number of these three possible numbers. So we'll type this in for the maximum, and we'll type this in for the minimum. Okay, so that's how you would do problem 6. Okay, problem 7, same kind of idea. We have f of x equals the natural log of x squared plus 3x plus 6 on the interval minus 2 to 1. So that's A, that's B. First thing we're going to do is come up with the derivative of this. So you might recall, if your function is 1 over... If your function is the natural log of g of x, the derivative is 1 over g of x times g prime of x. So we had studied this a little while back. So the derivative of this is just going to be 1 over everything inside parentheses. So it's x squared plus 3x plus 6 times the derivative of the inside stuff, which would be 2x plus 3. So the derivative is equal to 2x plus 3 over x squared plus 3x plus 6. Now we should see if the bottom factors, it does not, so there are no factors of 6 that add up to 3. And there's nothing we can factor out of the top, so we're just going to set both equal to 0 and see if we can find any critical values. Now there's no value of x that's going to make that bottom go to 0, so we're just going to look at the top. So we're going to say 2x plus 3 equals 0, or 2x equals negative 3, or x equals negative 3/2. So that's our critical value we're going to test. So we have 3 values to test. We have to test negative 2, which is f of a. We have to check negative 3/2, and that is it. So that is in the interval, so we should check that. This is minus 1.5. That is in between minus 2 and 1. Then we have to check 1. And if you plug in negative 2, you should get negative 2 will produce 2 natural log of 2. Negative 3/2 will produce natural log of 15 over 4. And f of 1 will produce natural log of 10. But again, what are these values? So we should come up with an approximate decimal equivalent. Natural log of 10 is 2.30. Let's see here. 15 over 4 is 1.34. 1.32. That's 15 over 4 in the natural log function, so don't forget that. 2 times natural log of 2 is 1.38. So they're pretty close, but this is the smallest, this is the biggest. So you're going to type this one and this one. Okay, and that would do it for problem 7. Okay, problem 8, we have a trig function here. So it says f of t is equal to 2 cosine t plus sine of 2t. And the interval is from 0, which is a, to pi over 2, which is b. First thing, find the derivative. So the derivative of cosine is minus sine, so this would be minus 2 sine t. The derivative of sine is cosine, but it's also going to be times the derivative of the inside, which is 2, so it's going to be 2 cosine of 2t. And we're going to set that equal to 0. But to do this, we're going to use a trig property that says this: cosine of 2t is equal to 1 minus 2 sine squared t. So we're going to get, we're replacing this with 0, so let me just plug in 0. 0 equals minus 2 sine t plus 2 times 1 minus 2 sine squared t. And we can divide everything by 2. Let's do that to be simpler. So we're going to get minus sine t plus 1 minus 2 sine squared t. And we are going to have, let me do a little rearranging here. So let's add 2 sine squared to both sides. Let's add sine t to both sides. And let's subtract 1 from both sides. So we have now 2 sine squared t plus sine t minus 1 equals 0. Well, this will factor into 2 sine t plus 1 sine t minus 1. And let me make sure I have my signs correct on that. Not quite, so this should have been the plus. And this one should be minus. Okay, so if you FOILed this, you'll get 2 sine squared t minus sine t plus 2 sine t, which is plus 1 sine t, minus 1 equals 0. So this is 0 when each bubble is 0. So 2 sine t minus 1 equals 0, which means sine t has to equal 1/2. This one is 0 when sine t plus 1 equals 0, or sine t equals minus 1. Well, sine t is 1/2 when t would be equal to pi over 6. And sine t is minus 1 when t is equal to 3 pi over 2. And you can look on unit circle to find those if you wanted to. Or just take an arc sine of both numbers and you'll get that in radians. But this is a good one where we have to think. 3 pi over 2 is not in the interval. So if the interval is from 0 to 90 degrees, 3 pi over 2 is 270 degrees. This one is not in the interval. It's not in 0 to pi over 2. So we don't have to check it, which is nice. Save a little work. So we just have to plug in 0 into the original function, which would be 2 cosine 0 plus sine of 0, 2 times 0. Well, cosine of 0 is 1, sine of 0 is 0, so this is just 2. Then we have to plug in pi over 6. And we'll get 2 cosine pi over 6 plus sine of 2 times pi over 6. And if you do that, you should get, this is equal to 3 square root 3 over 2, which is approximately equal to 2.60. Then the last one to check is the b value, the end of the interval. So we get 2 cosine of pi over 2 plus sine 2 times pi over 2. Cosine of pi over 2 is 0, and sine of pi is also 0, so this one should be also 0. Or not also 0, it's the first one that's 0. So if I look at these three numbers, I have 2 to check against 2.6 against 0. This is clearly the smallest, so it's the minimum. This one's clearly the biggest, it's the maximum. And so we have those two values right there. Okay, and that's problem 8. Okay, problem 9, another trig one. It says our function, f of t, is equal to 5t plus 5 cotangent of t over 2. And our interval is pi over 4 to 7 pi over 4. Okay, so we immediately find the derivative. Derivative of 5t is 5. The derivative of cotangent is negative cosecant. So this would be minus 5 cosecant squared of t over 2 times the derivative of 1/2 t, which is 1/2. So we get this is equal to 5 minus 5/2 cosecant squared of t over 2. And we're setting that equal to 0, so we're going to get 0 equals 5 minus 5/2 cosecant squared of t over 2. And we can move one term to one side, so we'll get 5/2 cosecant squared of t over 2 equals 5. 5 on both sides, so we can divide by 5 and multiply by 2, and we'll get cosecant squared of t over 2 equals 2. Or just multiply both sides by 2/5, same idea. Now take a square root of both sides. Cosecant of t over 2 equals plus or minus the square root of 2. And notice this interval, everything's positive, so I don't need this plus or minus here. I just need the positive version. So the interval has positive values, so this one's not going to count. So we're going to have instead of cosecant, we're going to do sine of t over 2, but we're going to change this to 1 over root 2, which is the same as root 2 over 2 when you rationalize the denominator. So when is sine equal to root 2 over 2? That occurs when its argument is either pi over 4 or 3 pi over 4. And multiply both sides by 2, and we're going to get t is equal to 2 pi over 4 or 6 pi over 4. And so we would have t can be either pi over 2 or 3 pi over 2. And both of those numbers are in the interval. So we're going to check both. So we're going to get f of pi over 4. We're going to check f of pi over 2. We're going to check f of 3 pi over 2. And we're going to check f of 7 pi over 4. Okay, if you plug these into the original equation, you should get pi over 4 is going to be 16. Pi over 2 is going to be, it's going to end up being 5 pi over 2 plus 5, which is approximately equal to 12.85. 3 pi over 2 is going to be 15 pi over 2 minus 5, which is approximately 18 point, my handwriting's messy here. I'll just say 18. I'm not sure what the decimal is. .6 or something like that. Okay, and then f of 7 pi over 4 is going to be 15.42. So if you look at this, this is clearly the smallest number, this is the biggest number. So we have, and you'd record this is your max and this is your min. Vice versa. This is your min and the bottom one is your max, which is what I have here. Okay, and that's going to be problem 9. Okay, problem 10, last one, also a trig problem. We have f of x is equal to 2x minus 4 cosine x from -2 to 0. That's A, that's B. Okay, now the derivative of this is 2 minus 4 times minus sine x, derivative of cosine x, double negative, so that's going to be 2 plus 4 sine x. Set that equal to 0. We're going to get 4 sine x equals -2. Divide by 4. Sine x is minus 2/4, which is minus 1/2. And sine x is minus 1/2 when x is -pi/6, which is in the interval. So that is in here. It's in between -2 and 0. So we just have to calculate the function when x is -2, the function when x is minus pi/6, and the original function when x is 0 from these the two interval values and the critical value pi/6. If you do this, you'll get -2 will produce -4 cosine 2 minus 4, which is approximately -2.34. F of -pi/6 will produce -2√3 minus pi/3, which is approximately -4.51. And when you plug in 0, you'll get -4. Now this is clearly the smallest, and this is actually the biggest. It's the least negative. So you'd have this is your maximum, and this right here is your minimum. Okay, and I know this can be a little tricky to get these trig functions exact values. So unit circle is your friend. So plug these values in the unit circle and you can see what sine and cosine are, or even in the last problem what cotangent is, and then you can get these as exact numbers and not decimals like your calculator is going to want to spit out. Okay, so with that, that completes Chapter 4, Section 1.